ArcGIS Pro provides tools for generating watersheds from digital elevation models, and we'll go through that here. So in the Analysis tab, you can look at Tools, and then in the Tools, go to Toolboxes, and down in the Spatial Analyst, most of the way down, there is a toolbox for hydrologic tools. So if I go to the Spatial Analyst tools and open it and go down, you can see that then there's hydrology tools. And in these hydrology tools, there's a list. And we ask you to apply these in an order. So basically, first you have to fill, then calculate the flow direction, then the flow accumulation, then you snap pour points, and then you calculate the watershed. So as described in the book and in the lectures, you fill to get rid of small pits, inconsistencies in the elevation because of the method, you know, from the readings on LiDAR or on other data development that lead to small sinks, that is, points that are lower than all the surrounding cells. Now, sometimes those need to be there. Those actually exist in real life. But if you want to calculate the watershed, you really want to include dams or subwatersheds. So the idea is that you identify a point low down on the branch, and with a filled DEM, which you may make a little bit inaccurate by filling, again as described in the reading, you calculate then the boundary of the inclusive area. And so we'll step through those here. Now I've loaded the digital elevation model and a hill shade on top of it. The hill shade here we don't really need, so I'm going to go ahead and remove it from this just to not clutter up the screen. So if I click on fill, there's just an input DEM and then an output, and I'll go ahead and take this fill drift. Now as described, the Z limit is a limit beyond which you won't fill if it's more than 2 meters or 3 meters or 5 meters deep. There's sometimes you want to leave those. Now we won't here, so there is no Z limit. It'll fill everything. And the fill runs fairly quickly. And so then here we have a filled DEM surface, and it should automatically load it when it's done. So it doesn't look too much different. And I could subtract the filled DEM from the DEM or vice versa to show the depth of the fill. I won't do that here because that uses tools you already know. So once I've done that fill, then I want to do the flow direction. And again, from class, you should know that, or from the readings and the lectures, that this calculates a direction from cell to cell flow. So it gives the downhill direction, but it quantizes it into those 8 directions, cardinal and subcardinal. So you basically get a set of numbers. And that's what this D8 flow direction type means. Again, you should know what that means. I'm just showing you how to do it mechanically using this flow direction tool. So again, we want to use our filled DEM because we fixed it, and then this creates this flow direction for the fill. We force the edge cells to go outward. That's useful because sometimes you can get in these circular endless loops on the edge. We don't need to now put drop raster that gives the drop from one cell to the next. Then we'll use this D8 flow direction type. There's others, again, options you should know from the readings and lectures. So I'll go ahead and run that, and it'll output this flow direction. And so those show the various cardinal and subcardinal directions here. So once I do the flow direction, then I want to do the flow accumulation. This gets the total flow into each cell following the cells downhill. So if I calculate the flow accumulation, I need a flow direction raster, right? So here's the flow direction raster I used, and a new flow accumulation. I'm not going to do a weight. Sometimes you have some cells weighted more than others for various reasons. Again, we're not going to do that. So we run for this flow accumulation, and we'll get this mostly dark with a few light squiggles out of these typically, because most of the cells have one to just a few cells or no cells draining into them, and then some of the cells, the one that receives the most, has tens of thousands or more depending on how big your raster is. So you typically get then this this branching pattern that's pretty faint and hard to see. So the next thing I want to do is snap the pour point. So I'm going to zoom to this layer. All right, so I'll zoom out to this layer, and you can see there down here at the bottom there is the ultimate outflow. And so if I just grab this and move up and zoom in, and then if I go ahead and in the map look at the Explore tool, if I go ahead and click on these points, it shows the values. So here off to the side, that cell only received 3 cells, and that received 0. It drains away, and that's 11. But as I reach down into this, I see that I'm getting these really large numbers. So I'm getting 1,604,600 cells, and down here at the very end is the very last cell. Now we ask you to create a pour point down here, and so what you'll need to do is create a new layer, a new point, and add a point on top of this low reach of the drainage. So we're not going to show you how to create a new point because you should, a new layer with a point in it, because you should have figured out how to do that before from previous labs. You'll be able to go back and do that. We'll just show that with one of those created, then you go ahead and do the snap pour point. Why do you have to snap the pour point? Well, because your outlet or your drainage point might not be exactly on this line, and when you calculate a watershed for a point, if it's offset, you just get this tiny watershed and not the whole one. So the algorithm goes through and takes your point and shifts it to the location on the line that's largest within its neighborhood. So here I've added a pour point file that I created. So you can see the pour point here is a little off to the side, and that's why we do the snap pour point. So if I double left click on the snap pour point, I have to tell what do I want to use as my input. So I'm going to do this, it's pout point actually, and you can use any value here. If you had multiple, you might have an ID. In this case, I'm just using a base object ID. And then the input flow accumulation raster, it's the only one I have, but I got to make sure I use the flow accumulation and not the flow direction. And then an output layer, and I give it a snap distance. Now, typically you want to keep that snap distance fairly small. In my case here, I'm going to make a snap distance of something like 9 meters and run it. And it should then create a new layer, this snap pout layer, and there it is, and there's my new snapped pour point. So you see it found in that 9 meter radius the largest flow accumulation value, and it moved that to my location on the line. So now I'm ready to use that as the basis for calculating my watershed. So again, back once I've done the pour point and snapped it, I go to the watershed, the D8 flow. We want to use the snap pour point as our input or feature pour point data. The pour point value field, that's fine. And then we have an output watershed raster, so we'll go ahead and run this. So now it has created an output watershed, and it's loaded it, but you can't really see it. So first I'm going to zoom to it, and well, okay, you get this big black area, but that's because of the things that it's piled on top of. So there's my watershed, and actually I did it so far down it's going off the page. I can put it up here a little higher. So here you have then this watershed, and we ask you to create the watershed as a vector, and so you have to export this, and those are up here in the conversion tools. We have you go from raster to a polygon. So the input raster is this watershed flow out. Field of value, we'll call this poly watershed, and run it. And now we get then this polygon.